Hi AP Calculus students, this is your first video for Friday's notes. So if you can please welcome your substitute to our class. All that we're doing today is wrapping up the last piece of section 7.2. So up until this point in chapter 7, this is what we've covered, this list that you have on your page. So your first section just dealt with area. So section 7.1, we had 2 different days in that particular section. And we talked about horizontal areas, so looking at things that sit above one another vertically. And then vertical areas, so where you have 2 different functions that you define in terms of y instead of in terms of x. Then after that, we've been doing volume operations, and so we've done a couple of different types of volume operations. We've done the disk method, which means you just have a solid circular cross-section. We've done the washer method, which means your cross-section is going to look more like a donut. And then we've done both of those operations both with respect to x and y, so both the x and y axis and then shifted axes that are either horizontal or vertical. So our last topic today, as your notes indicate, also involves volume. But this is the one piece of information about volume that we're going to get that does not come from a 3D circular rotation. Instead, what we're going to be using are the shapes of known cross sections. And so we'll be provided with information about a graph, and then we'll be provided information about the shape of a specific cross-section. Those 2 pieces of information put together can be used to construct a 3-dimensional solid, and one that we'll be able to find the volume of. So we're going to start off with an example, and we're going to take a look at this example and how it can be used to really discuss a couple of different interesting shapes. So we're going to start off with a cubic equation, y equals x cubed, and the line y equals 9x. So this is very similar to a graph pair that we had yesterday. I think we had x cubed and 4x for some of the y-axis work that we did. So it should be a very similar setup. Our cubic function is going to look something like this. That's my x cubed. And then my 9x, grab a ruler here and sketch that in. Going to look something like this. So we are interested really in this little area right in here. This is my y equals 9x right here. And as always, we want to know where things are intersecting. So I have an intersection at 0. And then, of course, I can always set these equal to one another. So I can say x cubed equals 9x. And then I can subtract over the 9x. I can factor out an x. X minus 9, x squared minus 9 is equal to 0. So my intersection points happen at x. And then x equals plus or minus 3. Now, technically, for some of the work that we're going to be doing a little bit later on, what I really want to do is constrain this to my first quadrant. And the problems that you'll be doing will have that information provided for you, so you know where it is that you're looking, and that way you're not dealing with 2 different regions. So I'm specifically looking at this area in between 0 and 3. So for part B, we want to find the area between those 2 curves. So in order to set that up, we're just doing an area integral. All we're going to do is use our integration bound. So we're going to go from 0 to 3. And then our upper function is the line. So our upper function is 9x. And we subtract off our lower function, which in this case is x cubed. And then if we wanted to integrate that out, our 9x would become 9x squared over 2. Our x cubed would become x to the 4th over 4. And we would plug in 0 and plug in 3. Now, once again, today our emphasis is going to be on integral setup, because at this point we are always able to just plug things into our calculator as long as it's a calculator-based operation. And even if it's not, you know how to do that kind of polynomial integration work or basic trig function or basic exponential function work here. So for the sake of time, to make sure we see all of the different kinds of representations of shape, we'll focus on that setup, and then I'll leave some of those integrals to you as an exercise, just to make sure that you're continuing to get that practice in. So we're interested in this particular area, but that's not anything new. That's stuff that we've been doing since the very beginning of chapter 7. So we want to move on to do something a little bit different, and that's where part C is going to come into play. Part C says, if the base of a solid is bounded by those regions, and those regions refer to the graphs that we talked about up in part A and B, and has cross-sectional areas that are squares, what will be the volume of the resultant solid? So, as what we've seen over the past couple of days, we talk about these kinds of scenarios in a few different lights. And so we're going to be graphing the same function a couple of different times. That way we can see it in different respects or kind of study different aspects of it. So our cubic function, I'm going to get that sketched out once more. I'm going to make it just a little bit bigger so that way we can zoom in on some key pieces. And then my 9x was this guy here. So we were interested in this region. Oops, that's intersecting at 0, 0, and this is intersecting at 3. So I'm still interested in this particular shape, but I'm no longer going to be interested in a two-dimensional area. I'm going to be interested in a three-dimensional volume, but it's not going to be a volume that's obtained by a 3D rotation. Instead, it's going to come from these cross-sectional areas. So we are told that the cross-sectional area that we're working with is going to be a square. So what that means is each of these pieces, each of these lines that I can draw between the upper line function and the lower cubic function is going to represent a square. So if you can imagine a square coming off of my page here, and if off of my page here, and here, and here, I can construct a three-dimensional solid this way. And visually, this is going to look quite a bit different than my three-dimensional solid would if I was constructing a rotational structure from a washer method problem. Now, as we talked about yesterday in class, my graphic skills are quite limited, so I will also provide some links online so that way you can see these structures a little bit better visually in a way that is much more artistically pleasing. So if we're interested in finding the volume of such a section where we're really just taking each of the distances here and calling that one side of the square so then we can bring it up to a three-dimensional volume, we're interested in what the area of a square is going to look like. So the area of a square is just its side squared. So if I want to transition from area to volume, what I'm going to do is take the integral of that side length squared with respect to whatever variable I'm operating with, which is going to be x in this case. And I'm going to go from the integration bounds where I intersect. So in this case, that's going to again be 0 to 3. So let's set that integral up. My volume is going to be the integral from 0 to 3. And then my side length is going to be what I have to get from my upper function to my lower function. So that was my 9x minus x cubed, that quantity squared, integrated with respect to x. So if you go ahead and plug that into your calculator, you can get a value out. You'll notice that this kind of volume does not involve pi because we're not doing any kind of circular rotation. So plug this in, see what you get, and I would recommend comparing that result with your desk partner or with the people around you just to see that you're all getting the same result when you plug that into your calculator. Then, part D, we're going to change our question up just a little bit. This says, if the base of the solid is bounded by those regions, so still the line in the cubic function from up above, and has cross-sectional areas that are equilateral triangles, what will be the volume of the resultant solid? So this time, still have that cubic function here. I still have this line intersecting. And it's still going from 0 to 3, so nothing's changing from time to time. But the difference here is now that I'm going to be constructing triangles as my cross sections that's going to bring it from a two-dimensional area to a three-dimensional volume instead of a square. So if you have equilateral triangles, that means they're all the same side, same size side. So I'm going to have one side here, but then that same distance here is going to kind of come off the page. And then same thing here. I'm going to have these three-dimensional structures that rise up. And each of the side lengths in between is going to then make the same values up above. So you can kind of imagine this coming off the page like this to make 3 dimensions there. Now, we always have to consider for each of the types of cross sections that we choose, what the corresponding area is going to be. So the area of an equilateral triangle isn't one that we necessarily have memorized. So what I recommend is if you go to Google and search area of an equilateral triangle, you can just find some of your formulas there. So it's going to be root 3 over 4, where A is your side length. So we've got root 3 over 4 times our side length squared. That's the area of an equilateral triangle. So if we want to translate that to a volume, we're going to integrate root 3 over 4 times our side length squared, and we're going to integrate with respect to x here. So our volume is going to look like this. We're still going from 0 to 3. And our side length actually hasn't changed from what we had up above. So our side length can still be found by subtracting our lower function from our upper function at a specific point. So that will become 9x minus x cubed, that quantity squared because we're squaring our side length and we're integrating with respect to x. That's our final answer on that one. And then we have one more type of shape that we're going to investigate here. This one says the base of the solid is bounded by still the same regions as above last time with these ones, but the cross-sectional areas are going to be formed by semicircles. So here's my cubic function. I think we're probably getting tired of this shape, so I apologize for kind of giving you that same wedge-like one over and over. But this is the region that we're looking at, still going from 0 to 3. But now the way that we're bringing the solid to 3 dimensions is that each of the cross sections is a semicircle. So this is the base of the semicircle, and then it's going to kind of come up like this. So this one is going to look kind of like a loaf of bread when it's raised up into 3 dimensions. You can kind of imagine these semicircles all connecting up here and then coming back down. So what we need to do then is think about the formula for a semicircle. So that's going to be pi r squared over 2. But what we have to think about is this is the radius up here. And so if we look at the region along the base here, this value going from the top function to the lower function is actually the diameter. So if we want to bring the cross-sectional area from 1 dimension or from our 2-dimensional area to a 3-dimensional volume, what we need to do is integrate. We're going to do pi r squared over 2, and we're going to integrate with respect to x. But since we don't have our radius, we have our diameter, we're going to have to divide that by 2. So our volume here is going to be the integral of pi, and then our radius we can call the same value that we've been using up to this point. So that's going to be our 9x minus x cubed. That's our diameter. We can divide that by 2, square that, and then divide the whole thing by 2, integrating with respect to x. And of course, this kind of work, just like any other volume-based work, is something where you can pull out constants from an integral. So I can pull out a pi over 2 before I even substitute in here. And then I could even bring out a 1 more 1/4 from squaring that piece. So if you prefer to look at it like this, where you bring the pi over 2 out to begin with, and then are integrating your radius squared, you can certainly do that too. So we're going to do this operation through with one more kind of shape. I'm also going to provide some links on the website, so if you want to check out how these shapes can translate so you can really visualize what's going on, then you'll have those for reference.